Today's video is going to be about congruence of integers. This concept is so cool. This thing was introduced to us by VOS in his monumental work. The few important properties: if A is congruent to B mod n and B is congruent to C mod n, then A is congruent to C mod n. This is called the transitive property. The last property is this: if A is congruent to B mod n, then A power k is congruent to B power k mod n. Okay, let's do some questions and you'll know. What is the remainder? Find the remainder when 1 factorial, 2 factorial till 100 factorial sum is divided by 2. Because this is an introduction, I want to dive even deeper into this subject. So let me know if some things are not clear. Hello everyone, welcome to this new video and last video of this week, of the first week of the beginning or the launch of this course. I'm really excited. It's been a beautiful journey. I hope you're all finding it helpful. I hope you're learning something new, right? So today's video is going to be about congruence of integers. This concept is so cool, like the coolest thing in number theory. So I enjoy this a lot because this makes so many things so much easier. So when you look at the problems, you'll understand what I mean. And this goes a lot longer, and so let's dive into it. Why am I not diving? This is not working. Okay, this thing was introduced to us by Gauss in his monumental work in the intro video, right, where I introduced you to the origins of number theory. I talked about the work of Gauss, this book. I'm not daring to pronounce it, so I hope you understand that this book was it's like very important. This changed, this revolutionized the way we look at the number theory as of today. And there maybe I don't know if he named it 4.1, but I picked it up from David Burton, so there it is, 4.1, where he defines this congruency. N be a fixed positive integer, two integers a and b are said to be congruent modulo n, symbolized by this. So this is not an equal to in between, this is a congruent to b mod n. That's how we say it, right? If n divides the difference between a and b, right? It is a minus b is k into n. So if we have, this is equivalent to saying a is equal to b plus some k into n. K can be positive, negative, anything, does not matter. This is the definition. This is the definition. Now why do we write like this if we can write like this? Because the k is not the important point for us. And later on, when we look at the properties of congruency of integers, we learn that the dependency on the k goes almost zero, like it's not important at all. Okay, so this definition, my dear friends, should be understood completely. Okay, let's move ahead. The few important properties, this is called reflexive property. Reflexive, where a is congruent to, this is actually congruent. A is congruent to a mod n, right? A is equal to a plus n into 0, right? So it works, no problem. If a is congruent to b, then b is congruent to a, because n divides a minus b also implies n divides b minus a. Understand? That shouldn't be hard to understand, because I mean, even if you write a is equal to b plus kn, it also means b is equal to a plus minus k into n, right? So this is called symmetric property, right? And the third one, if a is congruent to b mod n and b is congruent to c mod n, then a is congruent to c mod n. This is called the transitive property. Now tell me, where did we see the transitive recently? Where did we see the transitive property recently? We saw it somewhere, I think in the divisors part, right? Okay. So, A is equal to B plus n k and B is equal to C plus n L. That implies A is equal to C plus, so I will just replace this B over here. So, that will give me C plus n into k plus L, right? And you know, we learn about equivalence classes, we learn about equivalence relations. That probably we will do later on when it is required, but if a relation, if a congruency, right, if any relation between two numbers follows these three properties, reflexive, symmetric, transitive, it is called equivalence relation. Okay, is that clear? Now, if A is congruent to B mod n and C is congruent to D mod n, then A plus C. Okay. So, if we have A is equal to B plus n k and C is equal to D plus n L, then if you add, you know, this could be minus also, yeah, A plus or minus C is equal to B plus or minus D n k plus or minus L. So, it simply means A plus or minus C is congruent to B plus or minus D mod n. Yeah, and there are, it also says product is congruent mod n. So, again from this, if you take the product AC is equal to BD plus n into something, whatever this something be, isn't it? If you multiply these two expressions, you will get BD plus NKD plus NLB plus n square KL. That is what you will get. I will just take n common and I will write like this. So, that would imply that AC is congruent to BD mod n. Isn't that cool? I find it very interesting. Now, see, already the KL are getting very diminished, isn't it? Okay. Now, again there is another property that if A is congruent to B mod n, then if you add some constant or if you multiply some constant, it is always going to be the same. It's like multiplying a constant in an equation. So, if A is congruent to B mod n, so A is equal to B plus n k, then if you add C, nothing changes. I mean, n will still divide A plus C minus B plus C, right? Right? Nothing changes. And similarly, n divides A minus B would imply n will also divide C into A minus B. So, this is also followed, no problem. Is that understood? Clear? Okay. The last property is this: if A is congruent to B mod n, then A power k is congruent to B power k mod n. This is one of the most coolest properties, because this helps us do lot of things. Lot of things become very, very easy to do. So, if I have A is congruent, so that means A is equal to B plus n k. So, A power k, k I cannot use, maybe some L. A power k will be B power k plus, so if you know binomial theorem, you must know this. In fact, actually it follows from here itself. Here itself you see that AC is BD, right? You are just multiplying that. So you basically have a square is congruent to b square mod n, and similarly you multiply it with mod n, right? So you keep on multiplying and you'll still b remained with b power k mod n. So if you want to see some examples, let's look at some examples for everything. If okay, 31 is congruent to 1 mod 3. Then 31 power 5 is also congruent to 1 mod 3. Maybe that doesn't sound so cool, right? Okay, let's do some questions and you'll know. What is the remainder? Find the remainder when 1 factorial, 2 factorial till 100 factorial sum is divided by 12. Find. You can pause the video and you can find it. Now, one must note that factorial, first of all, what is factorial? N factorial is 1 into 2 into 3 into till n. This product is called n factorial, right? So, now if you look at 4 factorial already has a 12 in it, isn't it? Already has 12 because 1 into 2 into 3 into 4, this is 12. So 4 factorial is 0 mod 12, right? 4 factorial is 0 mod 12. Now that means if I take 5 factorial is simply 4 factorial times 5. Please notice this, which is congruent to 0 into 5 mod. So I always tell this, that when you take modulo, you are looking at numbers in terms of what is it being moduloed by. You are in the realm of 12, right? In the realm of 12, this carries 0 value because it is already multiplied, a multiple of 12, because the remainder is 0, isn't it? Is that understood? Okay. So how do we get now? So the rest of them will also have 0 mod 12, isn't it? So we just need to look at this. So this is simply 1 plus 2 plus 6, that's 9 mod 12. So the remainder will be, this should be remainder. Equal to 9. Yeah, I hope this is clear. We'll do more questions. I want to do a dedicated session on doing more problems on this. So hopefully next week's first session would be about problem solving, and I'll also include some of the homework, assignment problems which you might have doubts with, right? So please tell in the comments which question from the assignment you want to be covered in a problem solving session, right? Okay. Now show that 41 is a factor of 2 power 20 minus 1. Okay, so we essentially want to show 2 power 20 minus 1 is congruent to 0 mod 41, which is same as saying 2 power 20 is congruent to 1 mod 41. Okay. So how do we do that? So think about it. What is the nearest we can get to 41 in terms of powers of 2? What is the nearest? So I think if you take 2 power 6, it will be 64. It will be 64, which is 41 plus 23. Okay. Okay, maybe something simpler. Maybe 5 we can take. 2 power 5 is 32, which is 41 minus 9. Right? Yeah. So this is congruent to minus 9 mod 41. Now 2 power 20 is 2 power 5 whole power 4. That will be congruent to minus 9 whole power 4 mod 41. Would there be a simpler way? Oh yeah, I think we can just start with square instead of power 4. So if I square this will be 81 mod 41, which will be 40 mod. Now I want you to verify all of these results. I am just writing that down. I want you to verify that. Now let us look at this. So 2 power 5 whole square is congruent to 40 mod 41. Now what is 40 mod 41? Isn't this congruent to minus 1 mod 41? You can have negative numbers also, buddy. Negative numbers also allowed, buddy. Yeah? So that implies this is 2 power 10 now. So we want 2 power 20. If you square it again, this is congruent to 1 mod 41. Hence proved. Yeah? Is that clear? What is the time? Wow, today has been a very short session because this is an introduction. I want to dive even deeper into this subject. So let me know if some things are not clear. So now so far whatever we did, we used A is congruent to B mod n is equivalent to saying AC is congruent to BC mod n. But if we have this, can I cancel out C? Is the other way around true? No, not so. This is true only if C comma n is equal to 1. GCD of C and n is 1. Yeah. So how do we prove that? So if C comma n is equal to 1, that would imply that C is C x plus n y is equal to 1 for 1, and then we have AC is equal to BC plus NK. That would imply I will use see, I want you to show an example first, that 6 is congruent to 2 mod 4. That's correct, right? But can I cancel out 2? Can I cancel out 2 to say 3 is congruent to 1 mod 4? No, right? This is a big no. So why is that happening? That is because 2 comma 4, the thing which you are cancelling out, is not 1. But if I have something like 9 is congruent to no. Fifteen is congruent to let's say 30 mod 5. Now even if I cancel 3 to say 5 and to say 6, right, to say 10, sorry, even then this would remain the same. Yeah. So I'll cover in detail a few theorems in the next session along with some problems solely based on congruency, so that many of these concepts are clear. And right, I wish I could cover more stuff in today's session, but somehow I'm not feeling that well. So let's just like, share and subscribe. Yeah, shall we do that? I want to know how you actually feel about this series, how this series is going on, because without your knowledge I'm just speaking to the camera, right? I don't want to be that way. I want it to be a very interactive thing. So let's keep it that way, please. So I'll take your leave. Bye.